So this is actually the multi-level extension of the linear regression model. This first slide is just to, I insist on different notation than many other authors, including Hochside, discovered. So this is sort of a little legend to the differences in notation. I'm going to build this up in different stages. I'm going to start with what is known as a random effects analysis of variance model, which is a model where essentially the regression equivalent is you have your dependent variable and no predictors. Then I'm going to add predictors, level 1 predictors. And then in a third step, I'm going to add level 2 predictors as well. Actually, this strategy that I used to introduce these models is actually one that I also frequently use to estimate these models. So I often start out just with a random effects analysis of variance model, simply to get a sense of, well, what is the clustering in this data. So this random effects ANOVA, I'm going to introduce based on an example that I'll use throughout these slides. And this is a dependent variable that is basically a feeling thermometer rating for Barack Obama in 2008. The data are from the American National Election Studies 2008. And I'm interested in across-state variation in these ratings. Now, it's in some ways not a great example because we have only a limited number of states and probably too few to really do this well, but it's sort of for graphical purposes nice not to have too many of these units, so I will stick with it. So I'm interested in, well, do these feelings towards Obama vary across states? And one way to approach this would be to say, well, let's do a fixed effects analysis of variance. Treat each state as a group and then create a null hypothesis that says these group differences are 0 in the population and test it. And you can do that in terms of the setup by introducing again state dummies, and those are then the only predictors that you have in the model. And then you do an F-test on those dummies. The null hypothesis is the effect of each and every dummy is 0, and you test that hypothesis with an F-test. Now, that's not a terrible approach to the problem, but it's also not an optimal approach. There is something better that you can do. The problem here is if we really exhaust the population, so if we are in a position to control for each and every of the 50 states, then this would be perfectly fine. Or if the states that we have in our data set are the only ones that we find theoretically interesting, then we could also say effectively that is our population. But the way the ANES is organized, neither of these criteria is met, because what the ANES does in its sampling design is it ends up sampling counties essentially, but effectively that then produces a set of states. And there are 33 states that are included in the ANES on that basis, if you ignore the Washington, D.C. So this is an exhaustive population, and I also have no reason to believe that those 33 states are really the only ones I'm interested in. I mean, for example, Hawaii is not part of the sample. Well, does that mean because I'm not inherently interested in Hawaii? No, I am. It's just I don't happen to have that in my data set. Now, this is therefore something that we want to overcome. We want to actually sort of take into consideration the fact that the groups that we have, not just the individuals, but the groups are a product of random sampling sorts. And this actually is a tractable problem because we can draw our inspiration from experimental design. Because the typical experiment also consists of groups. Some of them receive a treatment, others of them receive a control. And sometimes in experimental design, the way we've organized this is that we can really say, well, these groups really are the only ones that I'm interested in. But sometimes it's a little bit different. So, for example, if you do a media experiment and you have intensity of exposure, so the control is you don't get exposed to the message at all, and treatment is you get exposed once, twice, 3 times. Well, these levels of exposure, they're somewhat arbitrary. Why not 100 times? And so you can think of that as being a sample. There's sort of a population of possible levels of exposure, and you've taken just some levels out of them. And that adds a source of variation, because we have random variation that is due to the individuals, but we now also have random variation that is due to the selection of the levels. And in random effects ANOVA, we can accommodate that. And that has a very long history in psychology that goes back much further than this side by Searle. It goes back to the 30s and 40s. So here is how that model works. We have an outcome of interest, y against subscripted in I and j, which is some outcome of interest, which varies across randomly selected individuals and groups. And let me say a little bit about the numbers here. We have J, capital J groups, and again, as I already mentioned earlier, we want that possibly to be very large. And then we have, in each group, n sub small j individuals. What is actually nice about multi-level modeling, just as an aside, is that this n sub j doesn't have to be the same in each group. You don't need to have the same number of Germans in your sample as Dutch or people from Malta. They can vary. And effectively, even if you design a survey for them to be the same due to missing data, they usually are not the same. It's not a problem. So we have this outcome y, ij, and now I start by writing something that I call the level 1 model. And the level 1 model is always stated in terms of the outcome variable. So we have yij here on the left-hand side, and just as another aside, you notice that I've moved from big Y to small y. This is sort of the random variable, big Y, and this is some realized value of the random variable. That's sort of what dictates whether I talk about big Y or small y. And this realized value of the dependent variable, I basically decompose into 2 things. A parameter beta 0j and an error term epsilon ij. And this parameter beta 0j, you see there's only a subscript j there. This picks up variation across groups. It's actually effectively a group mean. So in each group we have a group mean. That's how we would estimate it. Basically the sum of the y's divided by the sample size in a particular group. And then we have individual variation around that group mean that's captured by this epsilon ij. Does that make sense? And then we make an assumption. The assumption that we make is that this epsilon mean, you could substitute other assumptions, but this is the typical assumption we make, is that this epsilon ij follows a normal distribution. That's what this n stands for, with a mean of 0. So basically what we're saying is, on average, these deviations from the group mean are 0. And a variance that we don't know, and I call it sigma squared. And notice, and this is something that you could relax, but I will not play with, I did not put a subscript j here on the sigma squared. I assume that this individual variation across the observations is the same from one group to the next. Psychologists would call that homogeneity or variance. Econometricians would call that homoscedasticity. And you also call it constant variance. It just basically says that whatever varies across the groups is just the group mean, potentially, but not the variance around it. Now, that's the level 1 model. So it basically says you can predict an individual's response by considering the group mean, and if you really want to capture the exact response of that individual at that individual's error. Then the next part of this random effects model is to say, well, let's think of this beta 0j as a variable. That's sort of, at least if you're a frequentist, that's sort of how you have to think about it. Bayesians don't care, but this beta 0j, since it has a subscript j, you can think of it as a random variable. It basically means that it varies. It varies from one context, from one level 2 mean to the next. Well, and you can model it. I mean, if it's a variable, you can make it depend on the variable in the next equation and model it up. And that's what we do in this level 2 model. Level 2 models in general are always models of parameters. That's the left-hand side of the level 2 model is always the parameter. And this parameter in this case is beta 0j. And then we say, well, this beta 0j is equal to gamma 0, 0 plus delta 0j. And this gamma 0, 0, that is the grand mean. That's basically the mean over all groups and over all level 1 units. It's basically throw all your data together and just calculate the average. Plus delta 0j, and that tells us how the mean of a particular context, a particular group, deviates from that grand mean. That delta 0j could be positive in case the group mean is bigger than the grand mean. It could be negative in case the group mean is less than the grand mean. It could also in theory be 0, which means beta 0j equals gamma 0j. Does that make sense?
So the group mean would be then one of the groups, one of the, if we take the example of schools and pupils, one of the schools then?
Yeah.
And the grand mean is then the average over all the schools.
Yeah. So just a simple example I might illustrate this a little bit. So we have my J's here, and I have two individuals that belong to the first group, and I have three individuals that belong to the second group. And then I have say for my outcome variable y, say, a 0 and a 10 in the first group, and say a negative 10, a 0, and a 10 in the second group. So then the group mean in the first group is equal to 5. So if this was the population, then it would be beta 0, 1. We substitute the 1 for j here. And in my second group, the average in that group, negative 10 plus 0 plus 10, 0 divided by 3 is 0. That would be this beta 0, 2. So it makes sense? So beta 0, and then just substituting 2 for this j. And the grant mean would be equal to 0 plus 10 plus negative 10 plus 0 plus 10, so that's 10, if I'm not mistaken, divided by 5. So the grant mean, gamma 0, 0, would be 2. And then you could sort of say, okay, this beta 0, 1 is equal to this grant mean, 2, plus the error term for that particular group. But we know that this is 5. That means that for that particular group, the delta 0, 1 has to be 3. And for the second group, you would have 0 equals, did I do that correctly? Somehow I'm terrible at arithmetic, so I always mess something up. But then for the second group, you get 0 equals 2 plus delta, and then the delta for that individual would be, for that group would be negative 2. Does that make sense? So that's how it works. So that's the basic model. This is the random effects model, except we make an assumption about this delta 0j as well. Actually, we'll see the moment we make lots of assumptions in addition to what I have here. But just for now, we also assume that typically to be normally distributed with a mean of 0 and a variance that I will call tau sub 0, 0. The notation will become a little bit more clear when we go along. So what we actually are going to do now in terms of the estimation is we want to estimate this thing, the grant mean. We want to estimate the variance of the epsilons, and we want to estimate the variance of the deltas. So here is some more jargon. This gamma 0, 0 is known as a fixed effect because it literally is one value. There's no more variation there. The beta 0j is called a random effect. Actually, the epsilons and the deltas are also referred to as random effects. And the sigma square and the tau 0, 0 are variance components. So, general observations about this model, there are two sources of variation, the groups and the individuals. I already mentioned this. In general, the level 1 model is always stated in terms of the outcome, the level 2 model in terms of the parameters. And you can actually combine those two models quite easily by essentially substituting this level 2 model into this level 1 model. in which case you end up with this equation, yij is gamma 0, 0 plus delta 0j plus epsilon ij. That's then known as the mixed model. Because it mixes fixed and random phase, fixed, random. And sometimes what people do is actually call these last two terms, since they're both error terms of sorts, they sort of group them together, for example, in something you could call mu sub ij. Now, what would, say we want to actually think about Obama ratings and look at how they vary across states. If the hypothesis is that the ratings indeed vary across the states, then what we're effectively saying is that this delta 0j is a significant source of variation. In other words, when we go to the estimate of tau 0, 0, which is the variance of these delta zeros, then that should be significantly different from 0. Now, this model is not quite complete yet because we have to make some additional assumptions. And the most important one in some ways is the assumption of exchangeability. And exchangeability means that these delta zeros are driven by factors, things we don't observe, that are similar across contexts, which essentially means that we should have level 2 units that are comparable. We should not be comparing apples and oranges in a sense. And also operate independently between contexts. So we're actually assuming that the delta 0 for level 2 unit j and the delta 0 for level 2 unit k are independent. The correlation between them is 0. That's essentially what this says. The covariance between delta 0j and delta 0k is 0. Then we make additional assumptions. I mean, some of these I've already covered. So the level 1 errors are normally distributed with a mean of 0, a constant variance, and here too, this I did not explicitly mention yet, they are also not correlated with each other. So in a sense, when you look at the individuals within a particular cluster of context, we assume their observations to be independent from one another. The level 2 errors, this I think I mentioned. Everything, the level 2 errors are normally distributed. They have a mean of 0. They have a constant variance. There's no correlation, which is this assumption here. And then an additional assumption that I'm sure Chris will talk about to some extent because it plays a big role in full time series analysis, is that the level 1 and the level 2 errors are uncorrelated. In some ways, you're sort of saying, well, whatever the sources of variation, unobserved sources of variation at the individual level are, they have nothing to do with unobserved sources of variation at the context level, which is an assumption, a strong.
I have a question. Now the example you give is about the different states how they evaluate the Obama.
Yeah.
Imagine that we do the same thing for the primaries now, which are of course at a different time, which is of course a problem, but like hypothetically. There is like a correlation between, for example, the result of Iowa and the one of there could be one in South Carolina. Would that be a reason?
That would be a reason to question this assumption, to say, well, because you think about something like momentum, which these candidates gather, so you say, well, now Gingrich has garnered momentum, that will probably, for whatever reason, we may not know, and in this model we haven't specified any reason, that may carry over into the next primary. So that would then potentially cause discrimination. So that's something that you want to think about. Now, one way to possibly deal with that is to then, but you would have to do it in a different model than this really simple one, is to actually include measures. Because as we will see, if we actually sort of have a way to measure something like that, then maybe we could say, well, conditionally on having that measure in the model, delta 0 for one state and delta 1 for another state are independent. So, but in this particular model, there you're absolutely right, that would be the violation of the assumption. So, with all these assumptions in place, we can say something about the means, and we can say something about the variance and the covariance. First of all, we say something about the average of these random intercepts beta 0j. Since we assume that the deltas are on average 0, it means the average of these beta zeros is equal to the grand mean. So we're sort of saying, well, these groups are drawn from a distribution with a particular grand mean and some variation around that. And that variation then contributes to the observed values of the beta zeros that we would have. Except we don't really observe these things. There are also things we will have to estimate. And then for the y variable, we would say, well, if we average both over both level 2 and level 1 units, which is basically what I did here, then the average should be equal to grand mean. Now that's not so interesting. What is more interesting actually is the implied variances and covariances, which psychologists sometimes describe under the label compound symmetry. And I'm not going to show you where this comes from, but it's easy to show that the variance of the dependent variable, since there are two sources of variation, is actually equal to the sum of those two sources of variation. So we have variance due to individuals plus variance due to groups. And that's, of course, sort of interesting to note. This sort of starts to already give us a bit of an idea of how important these group differences are, because you sort of say, well, if tau 0, 0 is really small relative to sigma squared, then apparently most of the variation is due to individuals and relatively little due to groups. Which is actually what you very often find in survey research. And we'll talk more about that in a moment. Now the covariance, if I take two individuals who belong to different contexts, we assume their covariance to be 0. They're independent. So a German in my study and a Dutchman in my study have nothing in common. Two Germans do have something in common, and what they have in common, we can compute with this covariance. So we have the observation of individual I in context J, and Y for individual K in context L. And if J and L are the same context, so I might as well have substituted the J for this L, then the covariance between these observations is equal to tau 0, 0. That's what they have in common. That's sort of the common variation, just because they happen to be two terms. Now, with this information, we can calculate the interclass correlation. Because what is a correlation? Correlation, by definition, is the ratio of the covariance of the product of the standard deviations, and we have the ingredients for the standard deviations, and we have the covariance. And when we then actually compute this thing, we get a interclass correlation that is equal to the variance between groups over the total variance. And you can interpret this as, therefore, as the portion of the variance that is due to between group variation. So if there is no variation between the groups, because unlike this illustration, the group means are all the same, then tau 0, 0 is 0, rho is 0, which actually for the analysis would imply you might as well assume that you have set of independent observations. You don't have to worry about it. The other extreme that I mentioned, which you will never run into, but I'll mention it for the sake of completeness, is that there is no within-group variation. Sigma squared is 0. And that's the situation where all these Germans are exactly alike in terms of the dependent variable. In other words, both of these units would score 10, say all of these units would score a negative. In that case, rho is 1. And that effectively would mean that your effective sample size is really 1, because you think you have 1,000 Germans, but you could have done with just one of them. And you would have known everything you wanted to know about the dependent variable. There is no variation in the dependent variable. So let's go back to the example. And I'm not going to talk about how we get this stuff yet, but there's sort of two commands that we will work with in Stata, and I will send Fiona a do file so we can maybe distribute them. There is basically, for most of what we're going to do, we will use GLAM. And you can also use GLAM to do hierarchical linear models. The problem is it's very slow and you don't have to. So there is another option in Stata, I believe as a version 10, is an XT mixed option. And that you can use to do a random effects analysis or variance. And so the command is XT mixed. Then you specify the dependent variable. You could specify predictors here after Obama field, but we don't have any. It's a random effects ANOVA. Then you get these two vertical lines, and then you have to indicate here the level 2 unit, which in this case is the state. And then you have to specify a covariance structure. In this case, actually, it doesn't matter because there is no covariance. We will get into that in a moment. And actually, then I usually specify as an option var, which means that Stata actually reports the level 1 and level 2 error variances as variances, because by default it likes to report them as the square root of the variances, that is the standard deviations. So we get a grand mean of 64.05. So slightly favorable impressions of Obama. A lot of individual variation, 748.11 is the variance at the individual level, but also some sizable variation at the state level, 93.57. If you compute the interclass correlation, you find that it's about 11%. So about 11% of the variance in the feelings towards Obama is across states, and the remaining 89 is across individuals. Now, this is not uncommon to get that kind of distribution when you do an analysis with survey data, because remember, this error term, way back, this error term here, this captures omitted predictors, but it also captures measurement error in the dependent variable. And it's likely that we have quite a bit of measurement error in the dependent variable. So So that's what is partially creating this big variance, but it's probably also true that, I mean, different individuals have very different feelings towards them. Here is then my indication of beta zeros. And so this is the baseline, the group means, you could say. And you can see that they're highest in Illinois, which is not so surprising. Obama was senator from Illinois. They're lowest in Alabama, and then you sort of have a smaller in between. But they range really quite from below 50 to over 80. So there's quite a bit of variance when you think about it in these terms. Does this all make sense to you? Because now we're going to add a small complication, although we've opened a bit of a Pandora's box. But the complication is, look, we don't have any predictors here. This is a nice model if all you're interested in is asking the question, how much variance is due to states, how much is due to individuals. But we want to explain these things. So at a minimum, we want to have some explanatory variables at the individual level. Now, I'm going to keep this extremely simple for now, so I'm not going to pretend that what I have here is a good model of feelings towards Obama. In fact, you know it's not. But I'm particularly interested in the effect of a person's race. That's a dummy variable, coded one if the person is black, 0 if they're white. And I'm interested in what does that variable do in terms of the ratings of Obama, and at the same time I'm introducing some potential for quote-unquote causal heterogeneity, because I say, well, maybe race doesn't have the same effect in all of the states. Later I will actually add as an explanation for why the effect of race may matter differently across states. I will add as an explanation the percentage of blacks in the state. But for now, all I'm going to say, we have a model now with a predictor, race, and the effect of race can vary. In addition, we have an intercept to that model, and we allow that to vary. Now, the random effects ANOVA as such cannot accommodate these explanatory variables, but there is a literature in econometrics on random coefficient models, and they are perfectly suited for this. And they're a very straightforward extension of the random effects of ANOVA. And these models, too, have a very long legacy. If you sort of look at the history of multi-level analysis, what you will find is that a lot of the precursors to multi-level modeling are actually quite old. These random coefficient models in econometrics have been around since the early 1970s, mostly due to the work of Slamy. And there's a big literature on that. So let's look at this. We'll start here with what we would do in a simple normal regression. We'd say, well, we have a predictor X, race, and I would regress Y on race, and I would have a linear model with an intercept beta 0, a slope beta 1 associated with race, and this epsilon ij being an error term. Where then in a normal regression model, we would say that error term is normally distributed with a mean of 0 and a variance of sigma squared. And we would then go ahead and estimate beta 0, beta 1, and sigma squared. Now this is a pooled regression, because here all I say is the intercept is the same for everyone, the slope is the same for everyone, and what I want to do is relax those assumptions. I want to say the intercept the baseline level of support varies from state to state, and the effect of race varies from state to state. And in this particular case, actually, this intercept has a meaning, a very clear meaning, because this x that I'm dealing with here, this x is going to be 1 if the person is black, and 0 if the person is white. And so if you sort of look at what the equation looks like for white individuals, it becomes yij equals beta 1 plus beta 0 rather, plus epsilon ij. And for blacks, it becomes beta 0 plus beta 1 plus epsilon ij. And what I'm now going to do is I'm going to say, well, rather than assuming that this baseline level of support for whites is everywhere the same, rather than assuming that the effect of being black is everywhere the same, I'm going to let that vary. And that's what I've done here at the bottom. So all I've done to create the level 1 model here is add subscripts j to beta 0 and to beta 1. And that is then my level 1 model. Yij is beta 0 j plus beta 1 j times the predictor plus narrative. Now, that is sort of a fairly straightforward extension of the random effects of ANOVA. What is going to be a little bit more complicated is the fallout for the level 2 model, because instead of having one random component on the right hand side, I have now 2. So I'm going to have to formulate a level 2 model that actually has 2 equations. One for beta 0j and one for beta 1j. And in this random coefficient model, we actually don't account for why the intercepts vary or why the slopes vary. We just register that they may vary. So all we do is to create very simple equations here. We say beta 0j is equal to gamma 0, 0 plus delta 0j. That we recognize from the random effects ANOVA. And beta 1j is equal to gamma 1, 0 plus delta 1j. Basically what we're saying when everything is said and done is that the intercepts are drawn from a distribution with some common mean gamma 0, 0, and the slopes are drawn from a distribution with a common parameter gamma 1. Now, because we now have 2 equations, we can actually specify a fairly complicated error structure. We have 2 deltas now. And we want to, of course, estimate the variance for each of these deltas. But potentially we could also allow these deltas to be correlated with each other. Because we could say, well, maybe in places where the intercept is very high, the slope is very low. That would be a negative correlation between delta 0 and delta 1, or vice versa. If the intercept is high, the slope is also high, that would be a positive correlation. So to capture that, I have this error structure, and I'll walk you through this because this is probably not obvious. I stuck the 2 deltas together in a vector. And then I said, well, they're normally distributed. Actually, because I'm not talking about 2 random variables, the more proper expression is they follow a bivariate distribution. There's sort of 2 variables, and I specify a distribution over them, both of them simultaneously. So this n here actually means bivariate. The mean on each of one is 0. That's what this piece means. And then here we have covariance matrix that describes the rest of the bivariate normal distribution. And in this covariance matrix, the diagonals are the variances. So we have tau 0, 0, that's the variance of delta 0, j. And we have tau 1, 1, that's the variance of delta 1, j. And then to allow potentially that the intercepts and the slopes covary, I have a covariance here as well, a covariance component tau 0, 1. I could have specified an element here above the diagonal as well, but it would have been exactly that same covariance, so that's why I left it out. So that's the error structure that we have here. And that's quite it looks a lot more complicated, and sometimes it's also a lot more complicated to estimate, especially these covariances can give you headaches. We'll talk about that later. But that's the whole structure of the model. All eventually what it says is we have slopes that vary, we have intercepts that vary. The variation is specified through a bivariate normal with a particular covariance matrix, and these elements we want to estimate. So what we actually going to estimate in this model would be those two gammas, the three elements of this covariance matrix, and then this sigma squared for the level 1 error. Now you can also combine all of this into a mixed model. All you have to do is take these two level 2 equations and substitute them back into this expression. And then you get the mixed model, which in this case can be written as Yij equals gamma 0, 0 plus gamma 1, 0 xij. And then this complex looking error term that has delta 0j as the source of variation in the intercepts, delta 1j times xij as basically capturing fully the variation in the slopes. You see there's actually this multiplication with the actual values of the predictor that occurs, and then the level 1 error. And that's the model that we can estimate. And what it essentially tells us again, since we have exactly the same assumptions in the random effects in NOVA, what it says is the expectation of delta 0j is 0, so the random intercepts are drawn from a distribution with common intercept gamma 0, 0. We also have the random slopes being drawn from from a distribution with a common slope gamma 1, 0. Because also the errors epsilon are on average 0, if you want to look at sort of the mean, the predicted mean of the outcome, it's simply equal to gamma 0, 0 plus gamma 1, 0 times xij. So it's simply then equal to the fixed portion of the model. Now, in terms of the variance and the covariance, they are going to look more complicated than what we had before, because we have actually this delta 1 multiplied times the x's. So the x's are going to play a role in the variance and also in the covariance. With some algebra, you can then demonstrate that the variance of y is equal to the variance in the intercepts plus 2 times the predictor times the covariance between the intercepts and the slopes, plus the predictor squared times the variance in the slopes, plus the variance in epsilon. And for the covariance, what we're going to see is that that's equal, at least for units from the same context, that's equal to tau 0, 0, plus the sum of the values on their predictors times the covariance plus the product of their values times the variance in the slopes. That's just falling out of the assumptions we've made. But the important point here is that these variances and covariances are much, much different than what OLS tells us. OLS says variance in y is equal to sigma squared. And covariance is 0 everywhere. Every single observation is independent from the next observation. We see this is much more complicated, and again it introduces interclass correlation. This looks a lot more complicated, and in this case it's a function also of the values of predictors. So here is what I did in my example. What you see in that example is that we get then, to just look in, actually in this example, I need to explain something. In this example, I ended up not estimating this covariance. And why not? Because I don't think it was identified. And this is one of the things you have to be very careful about in multi-level analysis. Actually, it's much easier to detect these problems when you use GLAM than when you use XT-mix. With XT-mix, you can also make it up. But when I converted this variance-covariance matrix to a correlation matrix, I found that this estimate of the correlation between the intercepts and the slopes was essentially 1. And I don't believe that. I don't believe that whenever the intercept is high, the slope is also high. And that is often a sign that you're trying to ask something from the data and you can't do it. So then what I did is I went back and I basically said, okay, this is 0. And then you get these estimates that I put here. Pretty large variance in intercepts, pretty large variance in slopes as well. And then I was, of course, interested in next the question, okay, well, what do these slopes look like for race? And here I have the estimates of the beta 1 sub j's. And you see that actually the smallest effect of race is in Texas, and the highest effect of race is in Mississippi. The effects vary quite a bit. I mean, this picture actually may drive home a little bit better the variance than actually the estimate of variance component, because you see in Texas the effect is a little bit in the direction of, say, 21 or 22 points. So the gap between blacks and whites that you would predict in Texas is about 20 points, with blacks being 20 points more favorable towards Obama. But when you go to Mississippi, that gap is actually more in the direction of 37 points thereabouts. So that is quite a bit bigger, what you have there. And what is actually a bit unfortunate, and we'll talk about this, but this is actually often what you see people do in multi-level analysis. They just report this stuff, fixed effects, and actually, usually they don't even bother with varying slopes, they just have varying intercepts. Which I think is just an underutilization of the power of this tool, because this kind of information, at least in a linear modeling, could potentially also have gotten by basically running cluster corrected standard errors. What is so nice about what you can do here is that you can actually start looking at, okay, well, what is the effect of these predictors across the various contexts? And then, of course, in the next step, what we would like to do is to say, well, why is this slope for race in Texas so much smaller than it is in Mississippi. That would be then the next add-on to the law, which is where we head next. Does this still make sense? Yeah?
Can I ask a question? As you were talking about the covariance, we specify in state the covariance structured and unstructured. Is it what you meant with identified?
No, actually, that's a good point because I didn't show you what I did as the syntax there. So let me actually go back to the syntax we had earlier and just quickly explain to you what we would do differently. First thing we would do differently to specify this random intercept and slope model is we would add black after Obama field but before the comma. That just tells Stata that you have that added as a predictor. That there is a level 1 predictor in the model and you want to estimate its effect. Then the next thing that I ended up doing then is make one more modification to the syntax, and that is in this piece after those two vertical marks you have the state colon, and after the colon but before the second comma you would specify black, and that tells Stata that you want a variance component for the effect of black. If you don't add that, then all Stata will do is still just estimate a random intercept model, and it doesn't do a random slope model. So you need to add that piece here. And then you have to specify what this matrix with the tiles looks like. And what I have here is what I effectively ended up using in the second step in my estimation. I have covariance parentheses in them. And what that means is that you don't estimate a covariance between the slopes and the intercepts. If you want to estimate that covariance between the slopes and the intercept, then instead of typing in-depth here, you type unstructured for unstructured. And the syntax I will send you will see examples of all of those things. And also, which I did not explain either, with how did you get these random effects out of there. We will actually talk a little bit later about that. So that was the random effects model. And now we're almost to what is a proper hierarchical linear model. Namely, we now just add some predictions at the second level. We're going to come up with an explanation for why the intercepts and the slopes vary. In this case, I'm going to focus on the percentage of blacks. And because what we've so far discovered is that evaluations of Obama vary across states. That's probably no big surprise. That the effect of race on those evaluations varies across states. That's probably a bigger surprise. It's probably not something you would have expected. But we don't have an explanation for either phenomenon. Why are people in Alabama so negative about Obama compared to people in Illinois? Why is the effect of race in Texas so much smaller than the effect of the race in Mississippi? Now, of course, in principle, you could have different explanations for both of those things. And that's perfectly possible within multi-level analysis. To keep things simple for now, I'm going to use the same explanatory variable to account for the variation in intercepts and the slopes. So, and what I'm going to focus in on is the percentage of black people in the state. According to the most recent census, I think I used because it was closer to the election. I used, I think, the 2010 census data. I'm not entirely sure, actually, what I did there. So we want to take that attribute, which is now an attribute of the state, so it's all the subscript in J, and to make clear that it really is a different kind of attribute, I also use a different symbol for it, Z. How do we integrate that into the model? The answer is not all that different. The level 1 model we just leave alone. We don't need to do anything there. So the level 1 model is still going to be feelings towards Obama are equal to an intercept that can vary across states, plus the effect of race, which can also vary across states, plus a level 1 error term. What is different is how I specify the level 2 model. The only thing that I do differently in that level 2 model is instead of just having these gamma 0, 0 and gamma 1, 0, I add my predictor Zj with some effects attached. Gamma 0, 1 times Zj and gamma 1, 1 times Zj. We still have the error terms that we If you now substitute that level 2 model into the level 1 model, what you end up with is an equation that looks like this. Gamma 0, 0 plus gamma 0, 1 Zj plus gamma 1, 0 times Xij plus gamma 1, 1 Zj times Xij, which you should read as a multiple, plus delta 0j plus delta 1j Xij plus epsilon ij. It actually looks very similar to what we had before. The only thing we have changed is we have now a main effect of Zj, and we have an interaction between Zj and Xij. This interaction between Zj and Xij, that is known as a cross-level interaction, because we have a predictor at level 2 interacted with a predictor at level 1, so we're crossing levels. And this is a way to capture causal heterogeneity. I mean, the random coefficient model already captures random causal heterogeneity, but now we're actually offering an explanation for that. And that is often a very interesting part of multi-level analysis, is these cross-level interactions. How do they operate? What do we do with them? Now, the status of the level 2 errors also is a little bit different than in the random coefficient model, because now you should think of these delta zeros and delta 1s as residuals. Basically the variation in the intercepts and the slopes that is unaccounted for by this predictor Z. If this predictor Z is a really powerful predictor, then the variances associated with these deltas should basically be driven downward, and they may even become insignificant. And then I said here, we shall exploit this idea later to develop an R-square measure, and this morning as I was looking through my notes, I discovered that I skipped that part, so I will add it later on the board here. So, does that addition make sense? We will talk a lot more about how you interpret this cross-level interaction in a bit, but for now I think what is useful is to think about sort of just the idea of what it means to add these level 2 predictors and how that influences the model. So you basically introduce these level 2 predictors in a sense to account for the variation in the intercepts and the variations in the slopes. It's a bit like saying in this example I had before, why is the group mean here 5 and here 0? That's what you're trying to account for. Now, you can generalize this, but let's first look at what we get for this analysis here. We get the the cross-level interaction here gives us an estimate of 0.96. I haven't talked about significance yet, but it is significant, I think, at least at the 0.10 level. I'm not sure if it's any better than that. We will then do more of an explanation of what that interaction, this 0.96, does later today. Now let me, we also see that relative to what we had before, we see that we do see that the variance in the intercepts and the slopes goes down a bit. In fact, the variance in the slopes is basically gone. I think the estimate that I get in return there is something like 1 point something times 10 raised to the power negative 8. Now we can generalize this by saying, well, usually we have more than one level 1 predictor and more than one level 2 predictor. And then with P level 1 covariance, we can write this model as Yij equals beta 0j plus the sum of the effects times the values of predictors over all the predictors plus this level 1 error. And for the level 2 model, we could, in theory, specify an equation for each of these random effects. There will always be an intercept in these equations, possible explanatory variables, and then possibly an error term. And then if you throw this all together, you get this rather complex looking expression, but it's really not that hard to interpret what's going on. We have the overall intercept, we have the effects of the level 2 predictors, we have the main effects of the level 1 predictors, and we have the cross-level interactions and an error term. And likewise, the variance on y and covariance on y become much more complex looking expressions. Here is what they look like, but I'm not going to go in much detail. The same story as before. Basically, both of these are very different looking than what you would assume in ordinary least squares. And the important thing is that this would reduce to what we have in ordinary least squares only if basically all of the variance components at level 2 and the covariance components at level 2 are 0. Then this expression for the variance in y would reduce to sigma squared and the covariance would be 0.
Can I ask a quick question about the cross-level interactions? Would it be enough to have the blacks on level 1 and then the proportion of blacks in level 2? Why do we do the cross-level interaction? Is it necessary to interact with the level?
Well, the idea I had was maybe, and the effect that you get sort of speaks a little bit in that direction, that where the percentage of blacks is high, maybe the gap between whites and blacks is also bigger. That's what I sort of was thinking about. That you could give that as an interpretation as saying, well, maybe whites feel more threatened by Barack Obama if they live in a state with many blacks. And they think, well, black president, not such a good idea. I mean, that was sort of the assumption here. That's why I introduced it. But that's a theoretical point. I mean, and that's where you would have to say, okay, what do you think is important in terms of these cross-level interactions? And do you even want them? It's entirely possible that you don't have an explanation for the variation. It's also entirely possible that you don't have any reason to believe that there is variation in this effect. And then you wouldn't do any of these things. Sort of more like, okay, if I think that whites and blacks behave differently depending on the percentage of blacks, then I would introduce it through this cross. Does that make sense? I mean, that's just theoretically thinking. You can also say, well, maybe it produces a better fitting model, but that should be a secondary consideration.
Just wanted to ask whether you know any political science literature that uses the correlation between the random facts of the coefficient and the intercept to test the hypothesis, not to come up with an interpretation. So exactly hypothesize
No,
the correlational, like in educational science or...
no, very rarely. But actually, I don't know that many examples in political science where they do random slopes. It seems to be that people do a lot of random intercept models, but not much with random slopes. And when they do, it's usually sort of, well, let's allow for the correlation because it could be that there is some, but not that there is a real theoretical argument there.
So for example, how would you address the ceiling effect? So you have a positive high intercept.
Yeah.
And then my expectation would be that there will be some sort of ceiling effect. So I would expect more negative correlation between the random effects, the random slopes and the intercept.
Yeah.
So whether there is a correction for this.
That would be one argument to include it. Doesn't seem to work in this way. The correlation seems to be pushed to +1, which is weird, but that's why I didn't believe it. That would be one argument to do it. But I don't think there is as good theory as what you get in education on these things.
How much variance should we have in slopes before considering cross-level interactions? Because if there's no variance, there's no point in
Yeah, technically speaking, if you start with a random coefficient model and it turns out that there is no variation in the effect, then
there's no.
there should be no.
Just two last technical terms. So I have, for example, two random coefficients. And let's assume you have a theoretical background that you interact in the individual level.
Yeah.
Now, would that mean that you also need to specify, and then you have the two cross-level interactions between one second-level indicator and two covariates that were already on the first level interacted. So should you also do a cross-level interaction between the interaction term and your second-level covariate or not? Because that's really not clear in the literature. Some say only if it's theoretical. So let's assume that you had income and education, both have an effect on your dependent variable. Their effect is conditional.
Yeah.
Both vary across countries, for example. However, the conditional nature of the relationship between education and income varies across countries because of, I don't know, also public standing. So whether in this case you should model the cross-level interaction of the interaction term on the first level.
Yeah. There's, technically speaking, I would say yes. Practically speaking, I would say you're inviting a lot of headache if you do it, because very frequently, I mean, you already know that often you have collinearity between your interaction and your and the terms that make up the interaction. And if you now interact all of that with a level 2 variable, and now on top of that, say you also want to estimate variance and covariance components of all of that, then it gets really messy. I think that's more than anything the reason why people say, well, only if it's theoretically justified. From a statistical perspective, there's a good argument to include it. From a practical perspective, I would think twice about doing it. Because it gets really messy.
And also, if you have a limited number of level 2 observations, you risk having an unidentified equation, right?
Yeah, you would have to, I mean, it can happen there too, or at least you're really pushing the limits of what you can get out of an analysis. Now, in some cases, that is a bigger issue in a lot of cases, but I mean, that is something I will get back to, the sort of practical constraints on how you estimate these models. Now, I mean, what I depicted here in this complex looking equation is actually sort of the most general model you can come up with, where everything is random and everything has a cross-level interaction, which this is usually hopelessly unidentified. And what is probably going to be the case is that when you sort of look at the level 2 model, there will be cases where you will say, well, the thing isn't random at all. I have no reason to believe the effect to be variant across contexts. What you would do is basically just keep the constant and wipe out the rest of the equation, which basically means you set everything to 0. So say you do that for this first random effect beta 1j. You only keep the gamma 1, 0, you set gamma 1, 1 to gamma 1 cubed to 0, and you set the variance on delta 1 to 0. Or if you think it's random, it probably is not the case that all of the same predictors matter in each of these equations. So you can also constrain some of these gammas to make things a little bit easier. There are good reasons to do that. We'll get to that in a moment. Finally, just to give you a bit of a sense of what I actually, why I picked these subscripts on the gammas the way I do. It's probably sort of a pattern you can start to detect here. But the first subscript always corresponds to the number on the random coefficient. So we have beta 0, j, the first subscript on the gammas is always a 0. If we have beta 1j, the first subscript on the gammas is a 1. The second subscript can go from 0 to q. 0 is always picking up the intercept, versus the constant. And then beyond that, the second index on the gammas just refers to the number of the level 2 predictors. So gamma 0, 0 for the constant, gamma 0, 1 for the effect of the first predictor on the first random coefficient 0. That's how it works. So that's actually what I just said. I think, no, we have a break according to the schedule, which is perfect, then I can get to this in a while.